In this video we shall talk about concurrent transactions interaction. Once again we have to emphasize that for the next several solutions to work you have to execute each query in a separate session. That means that in most cases you may not use your typical client software, as it works in a single session even with multiple windows opened. But of course there are several solutions. You may either use console client for your DBMS and open several copies. Or you may write a simple program in your favorite programming language and launch one instance for each query. Now let's proceed with tasks, and in the first one we have to write a set of queries to demonstrate any data operation anomaly. If you read in Russian, please refer to this book to find extended solutions for all possible data anomalies. But for now we shall demonstrate only some of that anomalies, and the expected result for this task is the set of queries itself. In solution from MySQL we shall demonstrate dirty read problem. The idea of that problem is that one transaction modifies data, then other transaction reads that modification, and then the first transaction rolls back all changes. That means that these modifications will never be committed to database, but this transaction may access that data. So obviously here we need two transactions that will work simultaneously. In both of them we shall start with several preparations. First we have to detect the session ID and make sure that this ID and this ID are not the same. Then we have to turn off the auto-commit of implicit transactions, and then we have to set the transaction isolation level for each transaction. Then we are just starting both transactions and printing some debug messages. And then the main action starts. While this transaction is sleeping for 5 seconds, this transaction reads some data and then goes to sleep for 10 seconds. During that 10 seconds, this first transaction modifies some data, and then it goes to sleep for 20 seconds. After these 10 seconds, this transaction will read the data, and it will get the result of this modification. Finally, after these 20 seconds, this transaction will roll back its changes. So once again, these modifications were never committed to a database. So this operation of select, this operation of read returned dirty data. And one important thing to add, that for this example to work, you have to execute your transactions in a read and committed isolation level. To test this solution in MySQL, you have to create two SQL files, one for the first transaction and the second for the second one. Then you have to execute such a command file, and two console windows should appear. One window will contain that text and another will contain that text. Let's continue with Microsoft SQL Server, and here we have to make some preparations. We have to create two functions. The first one should produce the information about transaction isolation level in human readable form. The second one should produce the information about current time in convenient human readable form. And then we shall use these functions in the next code. With Microsoft SQL Server we shall demonstrate the lost update problem. This problem happens when one transaction modifies data and then another transaction modifies the same data. So this information, this update, is lost. Like in MySQL, here we have to start with some preparations. We have to detect session IDs and make sure that those IDs are not the same. We have to turn off the implicit transactions auto-commit. Then we have to set isolation levels for both of our transactions, and then we have to start our transactions. In the main part we see the following actions. This transaction sleeps for 5 seconds, while this transaction reads some data and then sleeps for 10 seconds. Then this transaction also reads the same data and sleeps for 10 seconds. And during that 10 seconds, this first transaction updates that data, changes that data. Then it also sleeps for 10 seconds, while this transaction changes the same data. You see that the first transaction commits its changes earlier than the second does. That's why these changes are committed in database for real, and these changes are lost. That's the lost update. To test this solution in Microsoft SQL Server, we may use the similar approach as for MySQL. We have to use two separate SQL files and then such a command file. And once you execute that file, you shall get two console windows with such a text in each. In the solution for Oracle, we also have to begin with some preparations. Here we also have to create a function to return the current isolation level name in human-readable form and to return current time in convenient human-readable form. Then in the main part of the solution we shall demonstrate the non-repeatable read problem. The idea of that problem is that when a transaction reads some data at the beginning of its execution and at the end of its execution, those data sets do not match. To demonstrate that idea, we also have to start with some preparations, and the most interesting part here is this update operator. I hope you remember that in Oracle we cannot start a transaction explicitly, but we may start a transaction by any data modification, like this. And then the main action begins. This transaction sleeps for 5 seconds while this reads a data. Then, while this transaction sleeps for 10 seconds, this transaction changes some data. And then it immediately commits its changes to the database. After these 10 seconds, this transaction reads the same data, but gets different results. So that's non-repeatable read. And to test this solution in Oracle, we may follow the same approach. As we have to create two files for the first and for the second transactions, and then we have to execute this command file. This action will lead to opening of two console windows that will contain that text with debug messages. In the second task, we have to write a set of queries to demonstrate mutual transactions lock. Of course, the expected result here is the set of queries itself, so let's look at that queries. Let's start with MySQL, and here we shall skip the detailed description of these preparations, as we've already reviewed all those details before. The main idea here is while this second transaction is sleeping for 3 seconds, this first transaction is changing data in books table. Then, while this transaction sleeps for 5 seconds, this transaction changes data in subscribers table. Then it sleeps again, and this transaction changes data in subscribers table too. And finally, this transaction changes data in books table. And here is the problem. This update waits for this update to complete. And this update waits for this update to complete. So the first transaction is waiting for the second transaction completion, and the second transaction is waiting for the first transaction completion. And that's the mutual transactions lock. All modern DBMSs detect that situation. To solve this situation, the DBMS has to choose a transaction randomly or by some algorithm, and then it has to kill that transaction. If you want to test this DBMS behavior yourself, you have to create two files for the first and the second transaction and then use such a command file. Once you execute that file, two console windows will open and one of them will contain such an error message. With Microsoft SQL Server, the general idea is the same. The only difference is that in this DBMS we may set the transaction priority. For instance, here we set high priority, here we set low priority. And that means that in case of mutual transactions lock, this transaction will become the victim. Then we are performing exactly the same operations as with MySQL. We are updating books table here and subscribers table here, then subscribers table here and books table here. And once again, this update waits for this update completion and this update waits for this update completion. So the first transaction waits for the second transaction completion and the second transaction waits for the first transaction completion. But as this transaction has low priority, the DBMS most likely select this one as victim and will terminate it. To test this behavior of Microsoft SQL Server, once again you have to create two files for the first and the second transaction, and then you have to execute such a script and two console windows will open and one of them will contain such an error message. And with Oracle the solution is exactly the same. We have to update this books table, this subscribers table, subscribers once again and books once again. And this update will wait for that update to complete, and this update will wait for that update to complete. And once again, the first transaction will wait for the second transaction completion, and vice versa, the second transaction will wait for the first transaction completion. As in Oracle we cannot set a transaction priority, this DBMS will choose a transaction randomly and kill one of them. To test this behavior of Oracle, once again you have to create two files for the first and for the second transaction, and then you have to execute such a command file. Then two console windows will open, and one of that windows will contain such an error message.